Alright, so I'm going to be talking about data-oriented design right now. Data-oriented design is almost a paradigm of focusing on data instead of focusing on objects, right? So a lot of the times when we're doing object-oriented programming, we're trying to create as many encapsulated objects as we can, right? So you take a small object and then you make it like a black box where you can't edit the data except for in specific ways. Try and make it secure, right? Sometimes that's a good idea. Sometimes it's not. Sometimes you want to actually make things a little bit faster. There's a reason for that. It's because cache misses are very slow, and when you have your data spread out everywhere across the heap, you're going to start getting cache misses left and right. It also classes have a lot of overhead, right? So if you're doing something like in the example here, where you have particles, right? Let's just say you have 50,000 particles. Having separate classes is just a bad idea. It's going to be very slow, right? And this is because, as a general trend, we see that's actually a logarithmic scale. Processor power has increased way more than memory or like disk storage, right? So if you're loading a file from disk, like it's going to take forever. If you're loading something from RAM, it's also going to take a very long time. But if you're just doing stuff on the CPU, it's totally fine. Everything's very fast, right? So you'd use data-oriented design when you're trying to process a lot of data, right? If you have like a particle or an animation system in the game, if you're doing some sort of data analysis that might take like 3 days and you want to reduce that to like a few hours, or if you're doing anything like with embedded hardware, you probably want to focus on making your data as clean as possible. So let's just take like a very basic example, right? We have a particle class in C++, right? And you have two 3D vectors. You have a position and a velocity for the particle, right? This is just moving in free space. It's not dealing with collision or anything. It's just a particle that's moving in a direction, and that's it. And it has a color too, right? So what do? You create a list of particles, and then you iterate over all of them, and you call update. And update will take your velocity and integrate it. So if you run this system and you keep on calling update, you're just going to see your particles moving in the direction that you set the velocity to. And that's all fine, right? This works. This is all encapsulated. Like, it'll be fine. Except there are a few issues here, right? So every time you call update, it will cache the entire particle, right? Unless it's already in the cache. And so what happens there is you're loading a bunch of unnecessary data. You're loading color right now, right? Why would you load color if you're not going to touch it for update at all? And on top of that, every single time you do that, there's a potential to have an iCache miss, right? Because you have, especially if this is a class that's like virtual, right? You're gonna have a V table, and that's gonna have to be loaded into cache, and you're gonna have to look up the method, and then also all of the data that you're using, right? If that's not already loaded in cache, you're gonna have data misses. Yeah.
Yes, C++. I don't think there would be a V table lookup since nothing's not.
Right. Yeah. Like I said, like if it were virtual, I mean, this is a very simple example, but I'm also like I'm using a simple example, but also pointing out stuff that happen in larger, more complicated systems. So like, if this struct was like, or if this class like had like 100 bytes of data, right, and your lines of cache are 64 bytes long, you're going to start having like data misses on the actual data and stuff like that. So yeah, I'm just kind of using a simple example. So the worst case, let's just say I've told the estimated amount of time it takes to pull something from RAM, right? Assuming worst case, it's a virtual method, you're going to hit the iCache miss. You're going to hit all of the data misses because position and velocity are like 100 bytes apart. And just everything's kind of, right? This is like worst case scenario. On average, I think for a console, was what I pulled it from. Reading from memory takes 600 cycles on the processor, and it should only take 1 cycle to add and only 1 cycle to move. So essentially what happens is, let's just say you're running the update method for 4 particles, like not even several thousand, just 4 particles. Worst case scenario, you're going to have like 7,000 cycles while only doing 24 cycles of like meaningful processing, right? So what do you do to reduce that, right? You don't worry about making a particle class. Particles are defined implicitly. You have a particle manager, and each particle is essentially an index into these set of lists. So what happens is all of your positions are stored together, all of your velocities are stored together, and all of your colors are stored together. So that when you go and call update, right? You're one, if assuming it were a virtual method, there's no longer an iCache miss, right? VTL doesn't have to be loaded or anything like that. It's just one method call. You're iterating over all the data, so it's cache friendly, right? The cache, when it sees a piece of data that it doesn't have yet, it will load all of the memory around it as well. So what happens is, as you load positions, you're loading a whole bunch of positions at once, right? And you just keep on, like, it's all there at once. You don't have to keep on loading and unloading from the cache. And then on top of that, all you're doing is you're reading the data sequentially, and that overflowed, whatever. You also minimize the number of data caches because, like I just said, all of your data is getting loaded into the cache at once, not one at a time. But there's still some minor inefficiencies here, right? So what happens is, because position and velocity, let's just assume those two are always being used at the same time, right? You're always updating position with velocity. The issue remaining here is that you have two separate lists, right? Those are going to be stored in two separate places in memory. If you have 50,000 particles, that's going to be like the entire size of your list of positions, and then your entire list of velocities. So those are separate. And the issue with that is now you're going to have potentially two cache misses, right? One for the position, one for the velocity. And it might load them sequentially, so you have the same chunks of the array in cache, but then whenever you move to the next chunk, you're gonna have two data misses instead of one. So we can still reduce that. And the idea is then you group your data based on what's going to be used together the most, right? So all you're doing here, all of the math is exactly the same. Everything you're doing is more or less the same. You're just moving around data. And yet we start seeing some massive performance benefits, right?
That change was, I guess, instead of two cache misses at once, it would just spread them out, but there'd still be the same number of cache misses in total?
Yeah, I guess it would just it would load both the positions and the velocities together, so it wouldn't be two at once. It'd just be like sequentially as it's going.
Yeah.
So it would load less into the cache at once, but you're not having two cache misses in a row. So I didn't actually run any numbers on this specific example, but other presentations have shown that with something like this, where you're just doing a lot of iterating and a lot of function calls, you can get like 2 to 4 times the performance increase. And there's a specific Sony presentation for the PS3 where they did this kind of an optimization for a scene graph, and they managed to go from 19.6 milliseconds for an update down to 4.8 milliseconds, and it can actually go down to 3.3 if you include prefetching, which is not something you can normally do on a computer, so I didn't include it here, right? And you're not really doing anything with the math, you're just changing where it's stored. It's just another way to look at how you rate your code, especially if it needs to be high performance. And it also lends itself to better design, right? If you want to send something over the network, all you do is you just send the length and then your array, and you're done. If you want to isolate actions, you can create static methods or just methods within your manager class, and then just run it over all of the data at once, right? You're separating your data from the actual actions that you're doing on them. So it's easier to set up with a test framework. It's just generally easier to work with, and it keeps your code simpler and easier to read as well. It's also very easy to make parallel, right? So multi-threading, all you have to do, you create a thread pool, right? One thread for every core in your computer, or however you want to manage that. And then you just divide your array of data into chunks, and you just say, okay, this array will deal with this chunk, this next array will deal with that chunk. Because all of these data points are independent, you should have no problem multi-threading this entire thing. Very simply, you don't have to worry about locking and unlocking objects. It's just a lot cleaner, right? That also helps you get a more like almost ideal performance improvement by adding parallelism to your code. So there's actually a lot of talks. Most of them are related to games because, you know, when you're doing an animation system where each character has like 100 bones, or if you're running a particle system with like Unreal Engine 4 does 500,000 now on the graphics card, like this is very important to do. So I'm going to include these slides. I'm going to email them to the list afterwards. So if anyone wants to actually like look more into this, these are some great starting points. And that's all I have to say today. Thanks to Goldschmidt, Morthy, Sean Sullivan, and you guys.